Welcome back, everyone. So now we have our contribution talks. So we have 3 talks in total. Each one will be 10 minutes long, 7 minutes presentation, 3 minutes Q&A. And the first one is towards interpretable reinforcement learning with constraint normalizing flow policies. So please go ahead.
Yeah, thanks for the introduction. So my name is Henriette, and I will be presenting this workshop paper of ours. And due to the relatively short time, I will skip a bit the motivation and jump right into it. So we want to solve continuous action space problems, so continuous control. And a very popular algorithm is, of course, soft actor critic. And as many of you know, it uses this so-called squashed Gaussian actor. This means you sample an action from a Gaussian, but the Gaussian has infinite support, so the action might be infeasible outside of your joint range. So you apply a 10H squashing to it, and then you obtain this action A prime, and that ends up being the action you execute. Maybe you rescale it into some other range, but we do the squashing, and of course we need to account for that as we compute the log likelihoods. So it's not really correct to just take this projected or squashed action and evaluate the likelihood of the Gaussian, because we have changed the random variable. And the soft actor critic paper tells us, yeah, we need to do this, but it's only in the appendix and they don't provide so much intuition for what's happening there. But if we visualize this, we can see it does the following. So we start off with this Gaussian, and then here is the 10H bound. And you can see that all the density that the Gaussian has that is outside of the bound is transported into the bound. And our nice Gaussian becomes this squashed Gaussian, which is really not a Gaussian anymore. But this is what this is doing, and it's called the change of variables formula. And this is a very useful piece of math if you want to manipulate policy distributions. So I want to talk about it a little bit. The change of variables formula says the following. If we have an invertible mapping function, so on some vector space, the invertible part just means we start at some point, we apply this mapping, we go to some point z prime, and then we can take the inverse of the function and get back our original point z. And with this change of variables formula, we can compute the transformed probability distribution. So this here is the original distribution, and then you can see that we are just scaling this with this weird term here, which is the Jacobian of this mapping function f. And this then gives us the corrected likelihood for our transformed random variable. And this is what SAG is doing there on the previous slide. So if we have these mapping functions, we can compute the density or the probability distribution of the transformed random variable. And we can generalize this to do it k times. So instead of doing only one transformation like SAG is doing, we can actually do many of them. And if all of these steps are invertible, we can still compute the final density of the transformed random variable with this formula. And actually, that is a normalizing flow. If you read the normalizing flow paper, that's exactly the equation. And the normalizing flow people use this to do variational inference. And so with this insight, we can appreciate a little bit that soft actor critic is kind of using a degenerate, like a one-step normalizing flow when they are applying this 10H squashing on the action space. And this is the key insight for us. We can actually exploit this formula because it allows us to do this k times with essentially arbitrary but invertible transformations on the action space. So we can manipulate our action space in a continuous setting with this. And that's very useful for constraint RL. So constraint RL just says, okay, in each state, some actions are forbidden according to some constraint function. So theoretically, we can do the following. We can start with the complete action space, and we can separate it into 2 sets, where one of them contains the action that satisfy the constraint, and the other ones are the ones that don't satisfy the constraints. And typically, RL lives in this MDP, so we are learning with the whole action space. But again, theoretically, we can just do this. We can construct an MDP that only has the allowed actions as the action space. And that's actually relatively trivial to do if you can evaluate a constraint function in the discrete setting, because you can just look at each action. But in a continuous action space, it's a bit more tricky. And in particular, it's not sufficient to simply sample an action, and if we don't like it, we resample, or we project it into this allowed action subspace. We cannot just change this action, because then the likelihood is not correct if we don't apply this change of variables formula. So my proposition with this workshop paper is to say, okay, if we have a constrained reinforcement learning problem, let's try to find this mapping function and then directly project our action space into this allowed action subspace and essentially learn directly in this nice constrained MDP where we are kind of safe or constrained or aligned by construction. So as a proof of concept now, I have the following result. 2D goal navigation, very simple. The actions are continuous translations. There are two constraints. The first one says the agent should maintain a sufficiently full battery. The second one is obstacle avoidance. So this is our nice environment. This is our agent here. That's the goal it should reach. This place is where it can charge the battery. This is supposed to indicate that the battery is relatively empty, and then there are some obstacles here. And I don't show here the full environment, but there is also more obstacles in the middle. So oftentimes the path to the goal is obstructed, which is here not the case. But yeah, so what we can do now is we start with this initial unbounded policy. This is a standard Gaussian, but it could also be a uniform distribution, doesn't matter. And I say, okay, well, my battery is empty. I apply some domain knowledge. I know here is the place where I can charge the battery. So I just say, okay, like the whole action space should go here. So to avoid confusion, this here is now on the axis. Maybe I should have labeled is the action space. And here's like a global view of the environment. But I can apply this formula, this change of variables formula, and move the whole action space and all the samples inside of this region. So now the agent, like no matter where it places the Gaussian, it will always be like pulled to this battery. And I can also say, okay, if I want to make sure that we are not executing actions that hit the obstacle, I can apply another transformation and move this thing, which now is already inside, but I can again change this action space to ensure it's for sure inside of this rectangle. So that's kind of the very constrained case. And if we are in a case where, okay, the battery is full, there is no obstacle, then these constraints are, or these regions are a lot larger, and they leave the most part of the action space for us, and we can actually optimize the task relatively unconstrained. So that's kind of the model we are proposing. We are starting again with a Gaussian like SAG, but instead of applying just one 10H, we are applying, in this case, like two squashing functions that ensure that we are aligned with respect to some constraints. And as like baseline results, I think this is quite interesting. So the first line, the red one here, is an unconstrained agent. So I disregard entirely that there are constraints and I simply lock them. And then we can see the dense reward function, the agent obtains optimal performance very quickly, but it requires high cost because I'm not punishing it for violating the constraints here. I just want to show the optimal behavior here is violating constraints. One way, very simple, of course, to account for this is to say, okay, if you violate a constraint, there is a high reward penalty. And we can see indeed then the agent learns quickly, or not so quickly, but learns to avoid transitions that violate the constraint. But the performance pretty much deteriorates because the large penalty dominates the behavior of the agent. Interesting is also the Lagrangian agent, which is a very common method to solve constrained MDPs. And we can also see, okay, there are violations in the beginning, but then it converges to like almost no violations, but it's very slow with learning the task. And with our model, we have no violations at all because we have applied domain knowledge to already construct this normalizing flow. And we solve the task very quickly because the search space is also reduced only to the allowed action subspace. So these are the results for the 2D example from the previous slide. And that's the only thing that's inside the workshop paper. So more thorough experiments where we have more complex environments where we maybe have to learn these transformations is to do. So that was it. So I would claim we can construct these safe, if your constraints mean safety, safe by construction policies by using normalizing flows. In my opinion, this is quite simple to implement because you just need to correct the log likelihood of your actions using this math that I have shown you, and you can integrate it into actor critic or policy gradient methods. You can apply some domain knowledge. So with these transformations, you can directly say, okay, in some states, these actions you cannot do or you should do like this subset of actions here. So you can kind of like shape the action space to help the agent. And then you sort of get an interpretable normalizing flow policy. Interpretable is a bit up for debate, but you can like inspect the different components of the model and you can see whether they actually result in satisfying the constraints. Yeah, so that was it. I want to investigate in the future how to learn these mapping functions for complex constraints. And yeah, thanks for your attention. If there are any questions, then I would gladly take them.
Yeah, thank you for that. We have time for one question. Please go ahead.
Hello?
Yeah.
Yeah, thanks for the very interesting talk. I just have a quick question. Do you think it would be feasible to incorporate the constraints into the dynamics instead of the action space? So for example, if I say my battery is too low, then the agent will reach for the battery, like for the charging station, and that's just the next state. That's the way the environment operates, and then the action space itself is unconstrained?
Yeah, I guess you could do something like that also. Is for sure different from how we are doing it here, because we want to manipulate this policy distribution. Of course, if you can maybe construct your environment in such a way that you automatically transition such that you don't violate constraints, I think that's also a good thing to do. And I think you could do it, but I think for that you don't need this math.
Okay, thank you.
Yeah, thanks.
Thank you so much.
Yeah.
Okay, so our next presentation is Adaptive Robot Navigation, a Human-Centered and Multi-Objective Approach with Demonstrations.
Yeah, warm welcome to my presentation, everyone. You already said the title. It's about a multi-objective reinforcement learning approach to robot navigation. My name is Yokohama, and I conduct my research at the Humanoid Robots Lab at the University of Bonn, that is headed by Maren Benewitz. So the motivation is that if you use an RL policy for robot navigation, and this is a very common practice nowadays, also in social robot navigation scenarios, the issue is that you define a certain reward function, and that reward function would bake the behavior of the reward function into the system. And the reward function is fixed and usually has some certain weights, and the behavior cannot be altered after training has finished. Then when you look at alignment, and you could do fine-tuning via reward models, that would usually also require retraining of the entire policy. And when you also want to incorporate demonstrations, I've done that a lot in previous works, those demonstrations might not be always adequate to reflect. So depending on the situation and on the context, you want to have a different behavior maybe. So wouldn't it be nice if we have, like in policy, that would instantly adapt to context and to preferences, and that would also make it very explainable, because if you have these preferences, it means that you can understand what's actually going on and what's being adapted. So the main contribution of this work is the following. We propose a multi-objective reinforcement learning navigation framework that enables policy adaptation after training has finished. And the demonstration data that we incorporate into the system is also now incorporated in a tunable manner, so you can turn it on and off. And lastly, we do an extensive qualitative and quantitative analysis, including a real-world transfer and also robot-to-robot transfer. I will focus here on the qualitative evaluation and the real-world results. With robot-to-robot also for quantitative, please come to the poster later on. So this is a picture of our architecture that is being proposed here. As you can see on the left-hand side, we have three different objectives that go into the system. The first one is demonstration data. The second one is distance keeping to human, which is a usual objective to have in a social navigation scenario. But then also for navigation efficiency is very important. And you can also see already that these objectives might be in conflict with each other. And this is also good that they are in conflict with each other. Those basically end up in a reward vector, and the reward vector is modulated by our preference vector here, lambda, and those are fed into the multi-objective reinforcement learning agent, which now observes the preference vector and also observes the state. So it's both input to the policy, and it outputs an action that is now adaptable. So for instance, here on the right-hand side, we see the environment, and there's different path trajectories colored here. So for the yellow trajectory, which is maximum efficiency, you would turn the efficiency preference all the way up. And then if you go to the distance preference, you would see that the trajectories start to have a larger distance to the human eventually. So the multi-objective navigation reward vector looks like this. We have, of course, our baseline navigation objectives. You always want to get to the goal, and you always want to avoid collisions. So this is a baseline term. And then the dynamic objectives that are tunable is demonstration, distance, and efficiency. The state and action space of the robot is containing the goal pose for the robot, so it's like a point navigation task, also the human pose, and we have 2D LiDAR for obstacle avoidance. Also, of course, the human would be seen by the 2D LiDAR. And the output is a continuous action space with angular and linear velocity. You can question, how do you now incorporate demonstration data? Well, previous approaches have done that with behavior cloning, but behavior cloning is not really natively to integrate into multi-objective reinforcement learning. Ideally, you want to just have a specific term in the reward vector. So now you can distill from demonstration data a reward model, but you will have the challenge that the demonstration data doesn't really have a ranking, and usually you would like to have sort of ranking data set to efficiently and nicely have a reward model. And that's being solved by an approach not developed by me, but by Brown et al. Called DREX, where first we have our synthetic demonstration trajectory that is being used here in the publication, which approaches the human, goes around in a circle, and then keeps on pursuing towards the goal. We can roll that out in the environment many times, also in different obstacle configurations. It's only use the trajectories that actually are collision-free. And from that, we train a behavior cloning policy. Now, the behavior cloning policy, we take and we roll it out in the environment, but at the same time, we also inject noise into it. And by injecting noise, you will get worse and worse behavior of that policy. And now you just do a simple ranking. You say, okay, if we have a trajectory with higher noise, that is less likely to be a demonstration trajectory, or further away from it, it has a lower ranking. And then you just use the Bradley-Terry model and train a reward model. For the qualitative results here, I will focus on the first column. So on the right-hand side, the preferences are indicated. We go from maximum efficiency to maximum distance here. And as you can see for the robot, while the maximum efficiency kind of cuts short on the human and goes towards the goal, while with increasing distance preference, we get higher distance to the human. As we go from maximum distance to maximum demonstration, we see that the black line here indicates actually the original demonstration, and we see that the robot in the red trajectories starts to resemble that demonstration trajectory, while it's not 100% perfect. So some information is lost along the way. And then when you go from maximum demonstration back to maximum efficiency, we see again that it starts cutting short on the human. And you see also that the objectives are in conflict with each other, so the trajectories are not exactly the same for different objectives. We did also real robot experiments here, both on the Turtlebot, which we trained the policy on in simulation, and the HSR robot. The Turtlebot had 360-degree LiDAR, the HSR only 270 degrees, and we just filled in the missing values at the back of the robot. So for the Turtlebot, we see a slightly oscillatory pattern here for the maximum distance preference, while the HSR is in fact a bit closer to the obstacle, but it has some wiggly motion before it gets to the goal. And the Turtlebot actually is much closer to the demonstration pattern compared to the HSR. And when we look at maximum efficiency, the efficiency is successfully reflected on both robots. But there seems to be some gap in the action space, some sim-to-real gap. Now a video also of that experiment, which you saw earlier on the plots. So here the Turtlebot is navigating around me, and we're starting to approach the maximum efficiency preference. You see now that it cuts short on me. Now we go from maximum efficiency back to maximum demonstration, and now it starts to do that circular motion around me, which was part of the demonstration pattern. And now we go back to maximum distance, and you see that the Turtlebot is starting to drive further away from me. The same thing has been done with the HSR in our robot-to-robot transfer here, and it behaves slightly different. So we again see the slight sim-to-real gap in the action space. Now here we come to maximum demonstration pattern, which was not as perfectly reflected as on the Turtlebot. And now we go back to maximum distance, and we see that the distance to the human is again increasing. So summary of the paper that I presented is that we have an approach that modulates conflicting objective, distance keeping, navigational efficiency, and demonstration data. We distill demonstration data into a reward model, which natively integrates into our multi-objective reinforcement learning approach. Then we do a successful sim-to-real and a robot-to-robot transfer. And our takeaway here is that multi-objective nature of this approach allows you to have a very human-centered integration into social environments and would allow in a feedback process for immediate adaptation of the policy without retraining. The limitations of this is that the demonstration data, once you've trained it into a reward model, itself cannot be altered after training. I think this would be a really interesting research avenue to go to. And the outlook is that you can now use this approach and enhance it on a hierarchical level, on a top level, with a context predictor, for example, that looks at a kitchen and says in a kitchen you want to have maximum distance to the human, or in the bedroom. That will work probably also with an LLM. And the tunability enables instantaneous adaptation in a human feedback process. Thanks, I'm happy to take any questions.
Are the 3 rewards are normalized? That also min and max reward you can get before the white scaling?
Yeah, good question. In fact, the reward must not be normalized due to the framework that I use, which is called PDMOL. It has some term that would actually figure out the different scales in the reward vector and normalize for it during training automatically, so you don't have to do it up front. But I would say it definitely helps. And the preference vector is convex, means that all of the individual terms sum up to 1.
All right, thanks.
I have just a quick question. How do you scale your approach to a more complex environment? Because at the moment you have a single person in the middle not moving. So once you have crowded environments, how will that work?
That's a very good question, in fact. So first of all, you have to ask yourself, what is preference in that case? So for most of my research, I defined like the preference to be on an individual basis. So you would have this robot navigating in the vicinity of a single human. Then if you have multiple humans, you might have like a family environment. You know, you want to reflect probably like the preference of the family. So you could have like an average preference here. You would have to account for that in the state space. So here I also include the position of the human. There are definitely approaches that allow you to incorporate varying number of human positions if you want to have that, but then you need human tracking, or you just go full sensor-based, which would also work, I guess. Yeah, and then if you go to full crowds, with preference, we're probably talking about like cultural differences, right? Different countries, and then you have averages with crowds. But this could also be then solved by the context predictor, which would on the fly adapt the policy to specific contexts. So that's really another, now it's a separate problem using that approach. Yeah.
Thank you.
You're welcome.
I guess, yeah, we can move to the last presentation, which is learning interactive viewpoint planning for foresighted object discovery using human preferences.
All right. Hello, everyone. My name is Nils Dengler, and I'm presenting today our work, Learning Interactive Viewpoint Planning for Foresighted Object Discovery, considering human preferences. So in this work, the goal is to map and shelf as complete as possible. And can you tell only from this image which objects are inside of it? Probably not, because in this scene there could be objects hidden behind the 2 large boxes, and just from a single image, we can't look behind them. And when using viewpoint planning for different perspectives, we could check several sides, but still the boxes are too restrictive to look behind them. So therefore, we could try to move one of the boxes to check behind it and include some actions, some physical action into it. However, it is important that this manipulation is done very carefully, maintaining the overall arrangement of the objects, which often tend to reflect human preferences. And consider this scenario where the robot needs to move the occluding box to observe objects behind it, and a push to the left could lead to a drop of the bottle, which is definitely not desired, and a push to the front would just rotate the box and eventually safely uncover the hidden can at the back of the shelf. And therefore, we developed a framework for object mapping and discovery in confined spaces, where we use viewpoint planning and minimally invasive push actions to reduce uncertainty and unveil hidden objects. Our system comprises a 2.5D occupancy height map, a reinforcement learning agent for viewpoint planning, and a push prediction network to determine the best action. All of this I will now elaborate on in more detail. So from an RGBD camera mounted on the robot's end effector, the acquired point cloud is projected onto a 2D occupancy grid map. And additionally, we record also the maximum height of each cell so that we can reason about different heights because larger objects tend to occlude more than smaller ones. And for the viewpoint planner, we trained a reinforcement learning agent, which uses as actions a space that was sampled in front of the shelf without any interaction inside the shelf. The reward consists of three terms. So first of all, the information gain that to minimize uncertainty inside the map. Then the motion cost to promote efficient and reachable viewpoints. And lastly, also a penalty for object collision of or object drops outside the shelf, which are obviously very restrictive. So we use the map's latent space and other relevant features, such as the last viewpoint and, for example, the center of the largest unknown space inside the map as observation, and the output is the next 5D viewpoint. Why 5D? Because the roll is very, not that interesting for us because it does not change the information gain. To uncover hidden areas behind large objects, we sample possible pushes via raycasting on the 2D map. And these push proposals are then fed into a prediction network that was trained in a supervised manner and suggests the best possible push. To train the network, we use binary labels that include the preferences and expertise regarding uncovered space, scene changes, and object contact due to their manually labeled by humans. In the left example here, you can see that a push would lead to more scene coverage, while the layout is only minimally changed since we already discovered the space at the end of the shelf. On the right side, on the right side, the push could damage the other objects since it would push the big box to the end of the shelf, and also it would just change the scene too much, while giving only minor benefits of increased space. So to summarize, our approach uses the occupancy map computed from the acquired point cloud for viewpoint planning and for the push prediction. And in the end, we use an heuristic action selection method that decides whether to continue viewpoint planning, perform a push, or if we want to end the mapping. So first, we evaluated our viewpoint planning without the pushing against two state-of-the-art methods for next best view and global planning. And due to their greedy behavior and nature, in this constrained case, our agent outperforms both in terms of the entropy reduction. Furthermore, the results of the real-world experiments are very close to the simulated ones, showcasing a very good sim-to-real transfer. To evaluate the complete viewpoint push pipeline, we tested the additional entropy reduction after several iterations containing also multiple pushes. In detail, we pushed like 4 to 5 times in a row. And we compared our trained push prediction network against a random push selection. And as can be seen, both achieve a high entropy reduction after carrying out those pushes. However, the higher entropy reduction of the random agent comes to the cost of large object displacement and falling objects. In contrast, our system has an object displacement which is 10 centimeters less and reduced object drops from 21 to just 4 in 100 trials. So to summarize, we showed an improved performance in comparison to the baselines regarding the entropy reduction and the object displacement. So here we come to a real-world experiment. First, the robot carries out the viewpoint planning and scans several poses. Then it tries to get the best push and decides for just pushing straight in the middle, which is, I would say, a quite good choice. And then it repeats this until it eventually uncovered the T-box at the end of the shelf, as you can see, and stops the exploration after that. So, and as current improvements, we utilize shape completion to gain more understanding of the scene. So we use segment anything to get the segmented labels of all objects, and then use the point TR network to get the shape completed of the current scene. And this completed and segmented clouds can then be used to generate an interactive 2D simulation that reflects the human preferences better than the binary labels could, and can be used for example, demonstration data, demonstration learning as data. Yes. So in summary, we showed an interactive viewpoint planning in confined spaces using minimally invasive pushing actions. The improved performance, we showed improved performance in comparison to the baselines, and the executed pushes highly benefit the viewpoint planning after executing them. For future work, we want to use the shape completion and for interactive 2D labeling. Thank you very much for your attention. For more information, you can check out the QR code or just come to the poster session later. Thank you very much.
Questions? I have one. So you are looking to minimize entropy as part of like trying to find. But does it mean you know exactly how much objects you have to locate, or?
No, we actually don't. We assume no prior knowledge at all, and not about the object number, nor the object models. So what we do is, when mapping, we just check if after several iterations, the information gain changes. Because if nothing changes after 3, 4, 5 iterations, we assume that everything is mapped.
Okay. And then how will that scale to more objects within the same space? Like a very crowded, I don't know, closet or cupboard.
So this is actually also the next step that we're investigating right now, also with like more with a better idea of how objects are placed, because currently we just randomly place them in there, but at some point we also want to reflect the human preferences in, for example, we always store the tomato cans close to each other and chips bags close to each other and so on. So we work on this, and the more crowded the shelf is, obviously the fewer actions we need for the viewpoint planning, but the more importance gets the pushing.
Okay, yeah. Thank you so much.
All right.